this new video on money in the packet problem solving. So let's just see what the problem says. So the problem says that there are n people standing in a queue, each of them having money M1, M2 up to Mn, right? So this M is denoting the money that is carried by the ith person. You are given Q queries in which you are given two integers L and X. For each query, you have to find a R where R is supposed to be greater than L such that the sum of the money from ML, ML plus 1, ML plus 2, so on and so forth till MR, sum of all these money values is equal to X. A note that has been given to us is there always and always exists an R for every query. So there will be definitely an answer for every query. So what we are expected to do is we will be given a number L and we will be given a number X. What we have to find a suitable R on the right side of L. That's why the R is expected to be greater than L. L is denoting an index. R is also going to denote an index. The sum of the money values from the person L, L plus 1, L plus 2, so on and so forth till R. Sum of all of these money values should be equal to the value X. The input format given to us is, in the first line of the input, we will be given two space separated integers N and Q, right? N is going to denote the number of persons, Q is going to denote the number of queries. The next line contains N space separated integers denoting M1, M2, so on and so forth, Mn, right? So in the next line, we are going to get N space separated integers, which is going to denote the money values that are carried by the ith person. This you can see in the form of an array. And the next line will be having Q queries, where they will be given to us as two space separated integers L and X for each query. The output format expected is that for each query, we need to find the value R. So the constraints of the problem that are going to be really very important for solving the question are the value of the length of the array, that is the number of persons can be as big as 10 raised to the power 5. The number of queries can be as big as 10 raised to the power 5. The value of money that is carried by any person can be as big as 10 raised to the power 9. L, which will be given, will be obviously greater than equal to 1 and less than equal to n. That means we are going to have this as 1 based indexing. And the value X, that is the sum of the values that we are expected to find, can be as big as 10 raised to the power 14. So if you see the sample input, you can find that there are 5 persons and there will be only one query. So the persons are having the money 1, 2, 3, 4, 5. So the value of L in the first query, the value of L is equals to 2 and the value of X is equals to 5. So we have to find an R such that starting from the Lth index till the Rth index, the money values are equal to X. So here you can see the answer is 3. That is, starting from the second index, you can just go to the third index, that is M of 2 plus M of 3, which is 2 plus 3, which is equals to 5. This value is equal to X, right? So this is the problem that we have to solve. I hope that you guys understood the problem. If this is the first time that you are solving this question, I would highly recommend you guys to stop the video here, think about the problem, definitely see the constraints that are given to you and try to solve within the given constraint, and then we will start the problem solving. So I hope that you guys have given a good thought about the problem, and let's just start solving the given question. So first of all, before we move ahead to the exact solution, let's see what can be the brute force solution to the given question, right? Because if you are able to derive the brute force solution, then maybe we can see some optimization within the brute force solution only that can help us to do some things. So let's just see. So what we are given is, we will be given an array like 1, 2, 3, 4, 5. This will be of length n, and we will be given Q queries, right? So let's say the query that was given to us, query number 1 was L is equals to 2, X is equals to 5, right? So what we can do is, in the brute force solution, that is pretty straightforward. What we can do, we can start from the Lth index, that is the second index in our case, and we can go to the right side of L one by one, one by one, one by one, and the next element, that whatever we are getting, we can add up with the value of L. So let's say what we can do, we can build a variable answer initially equals to 0. We can start from the Lth index. This index is 2, right? Let's say I write the index here. IDX as 1, 2, 3, 4, 5. So this is index 2, this is index 2. So I'll add the value of 2. So 0 plus 2. Then I'll move forward to index 3. This becomes 2 plus 3, which is equals to 5. And the moment we found an index, such that the sum of the values starting from the Lth index till that index is equal to the value x, we will stop. And this value of r is going to be our answer. So in a nutshell, we can start from the Lth index and keep on adding the values to the right till the time we find an index. Where the sum becomes equal to x, right? And this is exactly what is the expectation of the algorithm is also. That is, you need to find a value r, and r is always expected to be greater than L. So that's why we are going to the right side of L, and we are one by one adding the values. Now what will be the time complexity of the brute force solution? If let's say we are getting q queries, so for in each query what can happen is you can get a value of L as 1, and x can be so big that you have to iterate to all the elements, right? So in the worst case, what can happen is for each query, you might be going to all the indexes of the given array, and in the given array we are having n indexes. So the time complexity of this brute force solution is order of qn, right? This is the time. And the space complexity is going to be order of 1. This is going to be the space, because we are not taking any extra auxiliary space. Now the problem here is q can be as big as 10 raised to the power 5, as you have already seen in the constraints. N can be also as big as 10 raised to the power 5. Q into n will be approx 10 raised to the power 10. And we know that our permissible limit of 1 second is going to be 10 raised to the power 8 operations only. This is 10 raised to the power 10 operation. So the brute force solution is going to give you time limit exceeded. This brute force solution is going to give you time limit exceeded. But this is going to be a fairly simple one. So let me write a basic pseudo code at least for you guys. So what you can do is that while processing any query, so for let's say t is equals to 1, I'm writing kind of a pseudo code. T less than q less than equal to q, t plus plus, we are processing every query, right? And let's say in every query we'll take the input of L, we'll take the input of x, right? And then for I is equals to L, I less than n, I plus plus, will maintain an answer variable also and a sum variable also. Let's say we'll maintain sum as 0 and initially answer as L only. And then what we are going to do, we are going to do sum plus equals to A of I. If sum becomes equal to x, then what we are going to do, we are going to do answer is equals to I, and then we are going to break out of the loop and we'll do print answer. Right? So this is going to be the basic, I would say, pseudo code kind of a thing. That is, you are going to process each and every query. Here you are processing each and every query. For each query, you will get a value L and a value X. Then what we are going to do, we are going to initialize a sum variable. And an answer variable, we'll assume that the answer is initially L only. And then we'll start from L, we'll go at max till N. And one by one, we'll add up the values of the sum into the sum variable. If the sum becomes equal to X, then in that case, we have found an R which is greater than L to the right side of L. And answer becomes equals to I, that index where we have found it as an R. And we'll break out from the nearest loop, that is this for loop. And things are done. So there you can see this is a for loop going till q. This is a for loop that can in worst case can go to n. So the time complexity is order of qn. Right. So how to optimize? How to optimize? This is the question. Now, I'm going to give you one very, I would say, important advice that can be implementable in a lot of questions, right? So at any point of time, whenever in an array, we have to deal with contiguous cross-section sum, then making prefixes can help, right? This is going to be very, very important advice that I would like to give you, that at any point of time, if you are going to deal with somehow like some cross-section of the array, some continuous cross-section of the array, we have to calculate the sum or maybe the XOR kind of a thing, then making prefixes can help. So what I'm trying to say, let us see. Let's say we were given an array like this, A1, A2, A3, so on and so forth, AN, right? Now, let's say I want to get a sum from index I to index j, right? This is a function that returns sum from a of I till a of j, right? From starting from the ith index till jth index, you want to get the sum. So the brute force way to get this sum is one by one, start from the index I, do +1 +1 and go to the next index, and whatever is the element at the next index, add it in your sum variable. Do this till the time you reach the jth index. In this kind of an algorithm, the time complexity will be order of n to calculate the sum, right? Okay. But there can be a case that we have to calculate this sum multiple number of times. So let's say if you are having n number of times you have to calculate this sum, then this can become n square, because like every time you need order of n and you are calling this sum function n time, like you are having a lot of queries. So whenever we have a lot of queries and we are dealing with contiguous cross section of sum, then prefixes can help. So let me tell you. So what is a prefix sum? Prefix sum or cumulative sum, right? Prefix sum or cumulative sum, right? We need to see what is the prefix sum, what is cumulative sum. This is something that we need to figure out. Okay. So prefix sum means that if I write a function p that gives me a prefix sum till any index I, right, returns the prefix sum till I, then this value is going to be equal to A1 plus A2 plus A3, so on and so forth, plus A of I minus 1 plus A of I. This is prefix. This is what prefix is. Prefix is what? Some starting cross section of a given sequence, right? So prefix sum will be the sum of the starting cross section. When I say starting cross section, that is starting from the first index going till the ith index, we can sum up all the elements. This is the definition for the prefix sum, or let's say cumulative sum. Now if I know that there exists something called as prefix sum, then you can for sure think about the fact that if you want to write a function sum that can give you the sum from the index L to R, this can give you the sum of the elements from index L to R, then can I say this will be equal to prefix of R minus prefix of L minus 1? Can I say that? Just think about it. Let's say A1, A2, so on and so forth. Then there is AI plus 1, so on and so forth. AJ plus 1, so on and so forth. AN. Right. So you want the sum of this cross section. This is sum of L comma R. So you guys can tell me that if anyhow any cost, I can get you a sum of this cross section. This sum is what? This is prefix of R, and I can give you the sum of this cross section. This is what? This is prefix of L minus 1. So you have sum of this region and then you have sum of this region. If I subtract P of L minus 1 from P of R, so I can subtract this much part of the sum. So I will be left with this sum, which is equal to sum of L comma R. Can I say that? Let's just take an example. Let's say we have an array 1, 2, 3, 4, 5, 6, right? This is the given array. This is the given array, right? Let's say I want to calculate the prefix sum array. So prefix sum will be 1. This area will be having a prefix sum 3. 1 plus 2, that is 3, right? Okay. Then 1 plus 2 plus 3 will be equal to what? The prefix value of the last index plus the new value. So 3 plus 3, 6. This will be the prefix still here. 3 plus 2 plus 1. Then 6 plus 4 is 10. 10 plus 5 is 15. 15 plus 6 is 21. This is prefix array. This is prefix array. Right? Okay. Now you guys can see. If I want to calculate the sum from these three values, this sum is what? 5 plus 4, 9 plus 3, 12. And similarly, this 15 is denoting what? Sum from first index till the fifth index. 3 is denoting sum from first index till the second index. If I do 15 minus 3, this will be equal to 12. Can I say this is equal to the sum of 3, 4, 5? So this is what prefix sum leads to. Whenever you have contiguous cross section, then you can use this prefix sum, right? Now coming back to our question, in our brute force approach, what we were doing, in order to get a value to the right side of you, which is going to be equal to x, you are like summing up some values. So you are summing up some contiguous cross section starting from L, and you are trying to find the ending point R. So what I can say is, if let's say you are given an array A1, A2, so on and so forth, AI, so on and so forth, AJ, or let's call it AL, and AR, so on and so forth, AL, right? And you want to find, you are given AL, you want to find an R such that AL plus 1, AL plus 2, so on and so forth, A of R should be equal to X, right? We want to find such R, right? So A1, AL to AR can be also written as prefix of R minus prefix of L minus 1. This value should be equal to X. Can I say that? If we try to apply that same cumulative sum logic or the prefix sum logic, can I say that? Right. If we try to apply the same logic, then this thing will be done, right? This thing can exist. So that's what will be the gist of the problem. So what we can do is, we can say we want to find such an R such that it satisfies this equation. If it satisfies this equation, then if we try to simplify, prefix of R will be equal to X plus prefix of L minus 1. That is, we need to find an index R in the prefix sum such that its value is equal to X plus prefix of L minus 1. Okay. Now just think about it. Now the problem is reduced to this new problem. To find an R such that prefix of R is equals to X, that is the value given in the query, plus prefix of L minus 1. Okay. Now if you carefully see, then the prefixes, let's say 1, 2, 3, 4, 5. If we try to make the prefix sum array, this is 1, 3, 6, 10, 15, right? So if there are all positive values, then in that case, this prefix sum will be always increasing, right? No matter what do you have in the given array, if the array elements are always positive, then if the array elements are always positive, then the prefix sum array will be in increasing order, right? You have this also in increasing order, and when I say increasing order, that means this is sorted, right? That is, this is the smallest element, then the larger element, then again larger element, even larger element, because every value is positive in the given array and you are adding it to another positive value, so it is increasing the overall positive value. So what we have to do is, inside this prefix array, this is the prefix array, inside this prefix array, we have to find an R such that prefix of R is equals to X plus prefix of L minus 1. So that is kind of like inside this sorted array, I want to find the index such that the value at that index is equals to X plus prefix of L minus 1. And in a sorted array, if you want to find something can we use, let me write it here, can we use binary search? Right. I believe everyone knows about binary search. It's a searching algorithm that divides the search space into two halves such that one half of the search space is different based on some property from the other half, and it one by one reduces the search space and works in log n time. So what you can do, you can use binary search on this prefix sum array, which is actually a sorted array, in order to find an index r such that the value is equal to x plus prefix of l minus 1. You can use binary search on this array, and this binary search will be done in order of log n time. Can I say that? And in order to create this prefix sum array, you will require order of n time, and order of, this is order of n time and order of n space, right? As soon as you have done this order of n time task and order of n space task, that is a one time task. This prefix sum creation is a one time task. Whatever is the given array, you can create the prefix sum out of it, and then you can start one by one processing the queries, and each query can be answered using binary search in log n time, right? So the overall complexity of the problem will become order of n plus q log n, right? So n is going to be as big as 10 raised power 5, q can be as big as 10 raised power 5, and log of 10 raised power 5 is going to be approximately at 20. So this will be approx 2 into 10 raised power 5, sorry, 10 raised power 6, and this value will get submitted. This will not give you TLE. This is an efficient solution. Now the only thing left is how you can use binary search in order to find this value, and I guess that is pretty trivial, right? You can directly use the lower bound functionality. You can directly use the lower bound functionality in order to see that at which index this value x plus prefix of l minus 1 occurs for the very first time, because lower bound is going to, if let's say you try to do lower bound of x, it will give you the first index which is greater than or equal to x. So and as the question said, there will be always an r that satisfies the equation. That means this value will be always present here, and we will be able to find it in log n time. So just to repeat, we saw that if you have contiguous cross section that you are going to deal with, then what you can do, you can use cumulative sum or prefix sum. When you created prefix sum, you realize the fact that using prefix sum you can calculate sum of any sub array, or you can say any cross section of the array that is from L to R, which is using PR minus P of L minus 1. And what we have to do is we have to find such R such that A of L till A of R summation is equals to X. Now this value can be written in the form of prefix sum, which is prefix of R minus prefix of L minus 1 equals to X. We need to find one such R. So we can resolve this, and inside the prefix sum array is going to be always increasing because the values are always going to be positive. This is going to be an always increasing array. Increasing array means monotonic array, and inside monotonic array, if we have to find something, we can definitely use binary search. So we can try to apply binary search on the prefix sum array in order to find the value x plus p of L minus 1. We can use the lower bound algorithm of binary search in order to find it, and each query will be answered in log n time. The only extra overhead is the pre-processing time. So this pre-processing you have to do before answering the queries, that is create this prefix array. This prefix array can be created in very easily. This prefix array can be created in order of n time and order of n space. Order of n space to create the new array, and order of n time is because you have to just iterate on the normal array. As soon as you are done with the prefix sum task, then all the queries can be answered in log n time. So this will be the time complexity of the solution. So I hope that you guys were able to understand that what is the core intuition, that how we actually derive to the solution. This is not like that we directly jump to the solution. We step by step saw that where can we improve and how can we improve. Then we came to the solution. So now the last part is, let's just try to implement the coding implementation of the problem in JavaScript. Okay. So before we start the coding solution, I would highly recommend you guys to first attempt the coding solution on your own to see that are you able to apply the overall concepts of prefix sum, binary search, etc. or not. And if you have given a fair try, then let's just start. So first of all, we'll write the code for taking the input from the user, right? So first of all, we need to set up the standard input, right? And we need to set up the encoding to UTF-8. The standard input.resume is going to ensure that you are going to take more and more standard input from the standard input, and the set encoding is to ensure the fact that whatever entries you are giving as the input, all of them are getting converted to UTF-8 if not all, right? Then what we are going to do, we are going to keep an input string that is going to actually read the overall input, and we are going to keep one more variable, that is current line, which is going to store that at what line of the input we are at. Then what we are going to do, that is on standard input dot on event. So there is an on event, and whenever we get a data on that on event, what we are going to do, we are going to process the input string. What we are going to do in order to process the string is, we are going to trim the string. First of all, we are going to take the input. This input dot input stdin is going to take the input from the user and is going to append that input in the input string. Then what we are going to do is, as soon as the data from the standard input has ended, like the incoming data has ended, then what we are going to do, we are going to process that data which is stored in the input string variable. So like the process is like, whenever you keep on giving the input, the data event comes up in the on event, and we are going to store that in the input string. As soon as the user stops giving the input, in that case we hit the end event. Then we start processing the input string for getting the input. Then what we are going to do is, we are going to first of all trim the given input and then split the input based on new line. So every line is going to be split and getting converted into an array, stored inside an array. And then what we are going to do, we are going to read that array, and for every entry in that array, that entry is going to be the string. We are going to trim that string again. So this part is going to read the overall input. Okay. Then there will be a main function that we are going to call. So we'll be calling this main function from our stdin.on at the end event. Then we'll write a function readLine, which is going to read the lines one by one. So in the input string, whatever at the current line we are at, it will read that current line, and it will increment the current line pointer to the new line. Now here is the main logic that is going to happen. We are going to write a function lower bound. This lower bound function is going to take the prefix array, which is the increasing array on which we are going to apply the binary search, and it is also going to take the key which we are going to search inside the prefix array. You can see we have already discussed about the fact that we are going to search for x plus prefix of l minus 1. So this key will be passed like that. And then what we are going to do, first of all, let's just take the length of the array inside a variable. So we'll do let n equals to prefix dot length. We have stored the length of the given array. And then we will initialize two variables, that is I and j. I will start from 0, this is the lower part of the search space, and j will be equal to n, that is the higher part of the search space. And while I is less than n, that is while we have not converged the overall search space, we will calculate the mid, right? This will be equal to math.floor of I plus j by 2. This is, I guess, pretty trivial. And if the key that we are searching, if that key is less than or equal to the value which is present at the mid, then what we are going to do, we are going to set j is equals to mid, right? This k is denoting the mid. Else what we are going to do, we are going to do I is equals to k plus 1. That is, if the key that we are going to search, that key is less than or equal to the value at the middle index, then we need to converge to the left half, because we can find a value even better than that, right? Maybe there are contiguous same values, so we can find a value even to the left of that. Otherwise, we are going to converge to the right. And if the value of I is less than n, we have converged from the binary search, and the value is still less than key, we'll do I plus plus and return I. This is a typical lower bound function from the binary search. Then what we are going to do, we are going to write the main function that we have called above. In this main function, we are going to just take the input. So we are going to first take the input, that is the length of the array and the number of queries, right? That is going to be stored here. So n will be equal to the number of elements in the array. Q will be equal to the number of queries. We have extracted this from the input ARR. This input ARR has been extracted by reading a whole line from the input and then splitting it into two parts and then mapping it to n of q. Then what we are going to do, we are going to keep a prefix array which will be equal to of size n plus 1 initialized by all 0. And then what we are going to do, we are going to take another input of the new line, which is going to be the array, right? The array that has been given to us as the input. This we will store inside the input ARR at I. And when we are storing this array, then only we can construct the prefix sum. So you know that for prefix sum of I plus 1, if we already have the prefix sum till I, we can just add the I plus 1 of value. That is going to be pretty trivial, right? And then we are going to process all the queries. For each query, we are going to get two values, L and X. So here I'm denoting A by L, B with X, right? And then I can just call lower bound function with the prefix sum array and the value of the key as prefix of L minus 1, in our case prefix of A minus 1 plus B is denoting X, right? I guess there is a small mistake that we have to change K to mid everywhere, because this is going to denote mid in our lower bound function. You can see here, this should be mid, this should also be mid, this should also be mid, right? And I believe that is the whole implementation of the algorithm. Let's just try to run the algorithm and see if we are able to get our solution or not. So I've run the console. Let's say we are going to get an array of length 5. We are going to get one query. The array is like 1, 2, 3, 4, 5. And in the query, we are going to get L as 2 and X as 5. Here you can see we have given the whole input. Now to hit the event end, what you can do is you can press Ctrl D. That will give you the end of the standard input. So as soon as I press Ctrl D, see the answer is coming as 3. This D is due to the Ctrl D. So you can avoid that, but the basic answer is 3. That is the index is 3. That is 2 plus 3 is going to be equal to 5. So this solution has been implemented in order of q log n plus n time. N time will be taken here in order to construct the prefix sum array, and when we are processing, then for each query we are going to take order of q log n time, right? So I hope this coding implementation is clear to all of you and you enjoyed the overall question, right? I would highly recommend you guys to try the question once on your own so that you can get a better gist and better understanding of how to implement these binary search based questions. That being said, we will meet in the next video. Till then, take care guys, bye bye, and thank you.